On behalf of the Faculty of Mathematics, I would like to welcome you to the first Dirac Memorial Lecture. Paul Dirac was Lucasian Professor of Mathematics in this university from 1932 to 1969, a period of 37 years which witnessed tremendous developments in quantum field theory and elementary particle physics. St. John's College, of which Dirac was a fellow, in collaboration with the Faculty of Mathematics, has generously established the Dirac Lectures, which will be given annually within the field of theoretical physics, and particularly the field of quantum physics, which Dirac did so much to create. We are extremely fortunate to have Professor Richard Feynman here to deliver the first Dirac Lecture. Professor Feynman is Professor of Physics and has been at California Institute of Technology since 1951. His distinctions are far too many to enumerate, but among them there is the Einstein Award of 1954, the Nobel Prize of 1965. I think he's, of course, well known to every physics undergraduate of this university and indeed the world over for the Feynman Lectures of Physics, published in 1963 and standard reading in this university. Feynman is an outstanding physicist of the present generation, renowned for his work in quantum electrodynamics, liquid helium, and the theory of beta decay, and many other areas of theoretical physics. He lists among his interests in who's who Mayan hieroglyphics, opening safes, and playing bongo drums. A man with these interests can't be all bad. It's a great honor for me to introduce Professor Richard Feynman.
Does this thing work? When I was a young man, Dirac was my hero. He made a new breakthrough, a new method of doing physics, was to guess an equation. Previous to that, Maxwell got his equations, but only in an enormous mass of gear wheels and idlers and so forth in order to understand what he was doing. But Dirac had the courage to simply guess at the form of the equation and tried to interpret it afterwards. I feel very honored to, and I had to accept, after all, since he was my hero all the time, and I think it's kind of wonderful to have discovered myself giving a lecture in his honor. He was the first to, as he said, wed quantum mechanics and relativity together in his relativistic equation for the electron. At first he thought that it was the spin that you had to have was necessary, and that spin was a consequence of relativity. He also invented some ideas called Zitterbewegung and other things which turned out not to be very useful in the interpretation of the equation. But after some time, with the puzzle of the negative energies, he finally solved by filling them all up and making bubbles, which predicted the existence of antiparticles. And then it was realized that the idea that was necessary to wed quantum mechanics and relativity together was the existence of antiparticles. When that was added, you could do it with any spin, as Pauli and Weisskopf proved. And therefore, I want to start the other way about and start with the antiparticles and try to explain why there must be antiparticles if you try to put quantum mechanics with relativity. It also permits us to solve another problem which is very mysterious pre-relativistic times. One of the grand mysteries of the world is the Pauli exclusion principle, that when you exchange two particles, you should put in a minus sign. It's easy to demonstrate that in non-relativistic mechanics, if nature started that way, it'll be that way all the time. And so the problem would be pushed back to creation. And God knows how that was done. But with the existence of antiparticles, we make new pairs and therefore new electrons. And the mystery now is, why does the new electron that has just been made have to be antisymmetric with respect to the others and can't get into the same state as the others that are already there? And therefore, the existence of particles and antiparticles permits us to ask the question in a practical way. Suppose I make two new pairs with two electrons and I compare the amplitudes for when they annihilate directly or when they exchange before they annihilate. Why? Is there a minus sign? All these things have been solved a long time ago in a beautiful way, in fact, the simplest way, in the spirit of Dirac, with lots of symbols and operators and so on. And I'm going backwards to Maxwell's gear wheels, and I'm going to try to tell you as best I can what I think is a way of looking at these things so that they appear not so mysterious. I am adding nothing to what is known before, it's only exposition. So, here we go as to how things work, why there must be antiparticles. Ordinarily in quantum mechanics, if you have a certain disturbance on a particle which starts in a certain state phi naught, then it'll be changed, the state will be changed, and the amplitude that it ends up in a state chi is, as you all know, the projection of chi into A phi. There's a better Bra and Ket notation for that. We'll suppose that's true when we go to relativistic quantum mechanics too. Now suppose there are two disturbances, one at a time t1, A, and another at a later time, B, at time t2. And we would like to know what the amplitude is to restore the original state phi 0. The amplitude that we go from phi 0 to phi 0 is 1, the direct amplitude. And I'm doing this by perturbation theory. The next thing is the lowest order, in which first A goes into some intermediate state n, which lasts for a little time with the usual exponential. And then the intermediate state n is put into phi 0 by the operation B. This is the form in which two successive operations appear in quantum mechanics. Now, if A and B are local, that is, if they only exist in small area of space and time, they're not very widespread. We're going to make some simplifications. The way I'm going to do is first do very simple examples and then maybe talk a little bit more generally. I hope you understand the simple examples, because if you do, you'll understand all the generalities right away. At least that's the way I understand things. At any rate, one finds a term, the one plus the other term. In this case, suppose that the intermediate states are free particles of momentum p. And if they have momentum p, they'll have an energy given by their relativistic formula, which is the positive square root of p squared plus m squared. And these are the de Broglie waves which are rushing from point 1 to point 2 with momentum p and energy E. And we're going to suppose something. All the energies are positive. If the energies were negative, we know that we would solve all our problems, wouldn't we? We could keep dumping things into this pit of negative energy and get the extra energy out and run the world. But we know we can't do that, so we're going to suppose that all the energies in intermediate states are positive. Now here's a surprise. If we put together these waves with some amplitude that's any function of p whatsoever, this amplitude to get from 1 to 2 is not, and in fact it cannot be, 0 when 2 is outside of the light cone of 1. And that's a shock to anybody that doesn't know that if you started a series of waves out, they can't be confined in the light cone if the energies are always positive. And it's a very important thing, and it therefore must be the result of some sort of theorem. And so I made up a mathematical theorem, the proof of which I don't know, but I'm sure it's right in this application. That is, if we put together a function only with positive frequencies, defined this way, the integral only over positive omega, with any weights whatsoever, to produce a function of f of t, then that function cannot be zero for a finite interval of time. You see, ordinarily you're a little bit surprised there, because you know that you can take a piecewise function that's zero over a range in Fourier and analyze it, but then you'll get both positive and negative frequencies, and I'm insisting there only be positive frequencies. I got half as much data to work with, and I have two functions, the real part and the imaginary part of f, both be zero. Now, it may be that some clever mathematician can cook up some way that could almost happen with some kind of a e to the 1 over x or some terror, but I want it to be zero over an interval of time, you see, inside the light cone. And then if I change x, which changes all the phases and everything else, is still zero. I don't think you can make it work zero outside the light cone. So the point is, it's definitely so that this function cannot be zero outside the light cone. In other words, there's an amplitude for particles apparently to propagate faster than the speed of light, and no arrangement of superposition can get around that. Therefore, if time t2 is later than t1, we have an amplitude to have a connection like this in which a particle goes across faster than the speed of light. But because of the principles of relativistic invariance, there are axes. If these are separated by a space-like interval, there's a speed at which time t2 appears before time t1. Now, we're not changing the formula. We have this same process, but we're going to look at it from this other coordinate system, and what do we see? We see a process by which at 2, first thing that happens, see time is this way now, first thing that happens is a green thing and a black one come out, and later on the green one annihilates with the black one. To draw it turned a little bit, it'll look like this figure, which is a new process. This green line before used to go forwards, and now it's going backwards. So what we have to allow, and we have to include it in order to get any type of relativistic invariance at all, is a section of paths running backwards. The possibility of a production of a pair and an annihilation by a disturbance. In other words, there must be antiparticles. In fact, because of this difference of the coordinate systems in two different speeds, so that which is ahead of which depends upon which way you look at it, we can say this, that one man's virtual particle is another man's virtual antiparticle. Therefore, first of all, antiparticles in pair production must exist, and second, antiparticles' behavior is completely determined by particle behavior. There's absolutely no freedom. You know what the particle does, you know what the antiparticle does. How? You just look at it from the other end. Because one follows one way and the other way. To summarize this very crudely, and I'll do this very much more accurately and fancy later, if we reversed everything, we would reverse the sign of x, y, z, and t, then we should be using an antiparticle. I call C conjugate, charge conjugate, or whatever it is, the difference between a particle and an antiparticle. And this change of the sign of time and the three directions of space. Let P represent what's called the parity operator, which changes the three directions of space. So PT is C, right? But we're finished. We understand why they're antiparticles, and we understand that wonderful theorem that CPT leaves everything unchanged. Okay? And therefore, since I've already done what I said I would explain, why they're antiparticles, I'm finished with the lecture. But in order for that's all there is to it. It has to be that they're antiparticles in order to get relativity. In order to determine the sizes of the amplitudes, this didn't talk very much about the sizes. There are lots of relationships among the sizes of the amplitudes, and this leads us in a new direction in which we're going to get a clue about the connection of spin and statistics, because the antiparticles are making new particles, and we'll see how it works. And the key to that is another proposition, and is that the total probability, I don't never can spell probability right because I haven't got the patience, of all the possible events of all possible events always has to add up to 100%. But let us analyze this in the lowest order. Suppose there's a potential disturbance A. We already talked about how a particle coming in at momentum 1 can be deflected to some momentum p with some amplitude A. The absolute square of that is the probability of deflecting a particle to momentum p. Actually, I include in A the wave function coming up if you look back at it. Now, we can also calculate the probability of not doing anything. That is, to leave the object, the original particle, where it was before. And this is, the amplitude is 1 plus alpha, where alpha was that diagram that we made before. And the absolute square is this thing plus that thing. It's complex conjugate, I mean, because 1 plus alpha absolute square is 1 plus alpha star plus higher order. And so there's a definite connection in size and sign that has to be right so that these two terms that added together will cancel this. In other words, that these two add up to a negative amount. I left out a lot of i's and things like that in here. We'll always put them back if you want them, but the point is these two things have to be this, that the probability of not doing anything is reduced from 1 by the same amount as the probability of doing something is increased. All right? So that the sum of doing something and doing nothing is still 1. So that connects this size and sign and everything to that. We can prove this way that B has to be A star, but I don't need to bother you with that, so I won't bother you with that. Okay. Now, that was the non-relativistic case where we only had particles. Now we have a problem. We have added a new diagram, a new possibility. We not only have the 1 for the particle to go straight through, but the probability to do nothing is 1 plus twice the real part of this picture, which I'll call I, and twice the real part of this pair production picture, which I'll call Zwei. All right? Now, it's easy to check, very simple, that twice the real part of this one cancels the probability to make a transition from 0 to p. That works. That's just the same as it did before. What have we done, however, is we've added another piece, and so we have to find out what it is that this absolute square is correcting for. All right? Well, if you work out see, the size of this and that are completely determined. As we just pointed out several times, that particle and antiparticle are absolutely related. So the size of this is completely determined. And this thing, you can work out, I'm talking about spin 0 particles now, it cancels the probability to make a pair with the electrons in O and the antiparticle has momentum p. That is to say, this is the negative of this probability. Now, what does that mean? You see, that's easy. You say these are all the probabilities of producing pairs, but it isn't really, because you could produce pairs with any moment for the electron. And that's all canceled by something else, which is in a vacuum that we can come back to. But here is a special case in which we produce a pair with the electron in the same state as O. We have somehow, in order to make this all work, because this is a negative contribution, to say, in order to make it consistent, it has to come out that the probability of producing a pair with an electron in O is enhanced when there's an electron present in O. And that enhancement is what's being canceled. And that's the principle of Bose statistics that makes the lasers work. That if there's a particle in the given state, the probability of producing a new particle is increased. It's doubled, in fact. And this extra 1, 2 is 1 and 1. The extra 1 is the thing that's canceled by this, and that's how it balances. And so we can get a clue as to why the Bose statistics are the statistics for spin 0. All right? Now let me just outline it again. We've added an extra diagram, told us about a new process called pair production. We discover when we try to check the probabilities that this diagram makes a negative contribution. We have to cancel something, And that canceling is an extra probability for producing an antiparticle and an electron in the state O when there's a particle present originally in state O. And that phenomenon, that when there's a particle already present, the probability of producing another one is enhanced, is a characteristic of Bose statistics. And that's where it begins. That's to explain to you why it's possible. And if all you have to do is follow more details, more diagrams, more cases, and the whole thing will come pouring out. I've just given an example to show you which direction we're going to go. I'll just do one little example. If we didn't have any particle but started in a vacuum, then you can make a pair Q and P. And the probability to make, you see, you can make pair production, so that makes a particle Q and P. And the probability to make those pairs is sum over all Q and P of this absolute square. And that must be compared to the amplitude to do nothing. And the way that you balance that one is that you have another diagram in which you created a pair and then annihilated it. And if you take minus twice the real part of that, or rather, twice the real part of that is the negative of this. And so that's the way that balances. And the extra diagram we saw on the previous page is extra and on top of that. So here's how all the pairs balance. And to finish it all off, what happens is that you find that you have to add all diagrams together. And you can see the exclusion principle with the positive sign this way. Suppose you had 4 disturbing potentials and you produced 2 electrons with their positrons, and they annihilated again. And now suppose you compared that to what would happen if you produced these 2 pair, but instead of annihilating their own positron, they went across and annihilated the other guy's positron. That would make a figure like this. Well, this is a single loop, you see, and these are 2 loops, and you're supposed to add all the diagrams, so you add this and that, and it'll all fit together, and everybody knows that, and it's very simple, and it makes Bose statistics. Bose statistics, as a matter of fact, is not so very mysterious. As soon as we deal with anything like oscillators, such as the vibrations of a crystal, which makes sound waves, we find that those sound waves obey Bose statistics, then we're adding all the amplitudes together. And so we don't find that quite as bad. What we're going to do is we're going to discover later that for each loop, when the spin is a half, each loop gets a minus sign. And therefore this has 2 minus signs for this 2 loops multiplied together, which is plus, and this is a single loop, which is minus. So when we change to 2 loops to 1 loop, we change from 2 minus signs multiplied to 1, and it's an opposite sign, and you get Fermi statistics. So I'm just focusing now. We have to look and understand why, with spin a half, we're going to understand later why there's a minus sign in the formula for the loops. Okay? Now I'm going to return now, because I have to be more careful, to go a little bit more into detail and to explain the relationship between the antiparticle behavior and the particle behavior. Of course, it's true, and it's still true, that the antiparticle is completely determined by the particle behavior. Let me analyze this a little bit more in detail in the case of spin 0. We noticed that for T2 greater than T1, that is above the plane here, the amplitude to go between 1 and 2 was this integral. I've chosen a special case of scalar couplings and so on because this form is relativistically invariant. The 2EP under the D3P makes a relativistic invariant volume element in momentum and energy. You have to check that someday. This E, energy times time minus momentum times position, is of course the typical relativistic combination of the product of the time components minus the product of the space components. And this is a relativistically invariant form, and I've chosen that one to study. Now, because that plane could have been taken anywhere, we know that all over the outside light cone, if I just tilt the plane, if you want this point here, tilt the plane far enough down, take the coordinate system this way, and you'll get this function. It's always the same function because it's relativistically invariant. So this function is not only true above the plane t equals 0, it's true of the whole negative light outside the back light cone. That is, the space-like region and the future light cone. This formula is right. On the other hand, for t less than t1, and also space-like separated, since energy must be greater than 0 always, we have to have a form that the same amplitude is g21, I mean the amplitude in that region, either t2 less than t1 in the bottom light cone, or else inside with t2 less than t1, but in the space-like region, we'll have to have the opposite sign frequency with a whole lot of weights all added together in some complicated way. The question is, and in the region when T2 and T1 is space-like, we could use either one of these two formulas to obtain the amplitude. It's like a patching, and that makes the functions have to be equal there, and that's going to determine what this function has to be, this G, because we know it's equal F in that region. So the question is, if a T2 and T1 space-like, we have an expression with a negative frequency, can we express it also as a function of positive frequencies alone? Ordinarily, you can't do it. It's magic, but for this particular function, which is relativistically invariant, it's possible. Let me show you why. First, for T2 equal T1, F21 is real, because this isn't here. And when you integrate over P, you have both positive and negative P, and the complex conjugate is just the negative P, so you average both when you integrate, and it's real. F is real. But F is relativistically invariant, and if it was real for the 2 times equal, in another system, the 2 times are equal somewhere else, and so forth, and therefore, since it's relativistically invariant, it must be real for any T2 and T1 which are space-like separated. Fun. Now, since it's real for any T2 and T1 space-like separated, it's equal to its complex conjugate if T2 and T1 is space-like separated. And therefore, one solution is that G is the complex conjugate of F that has the right sign on the frequencies and that's equal to F in the space-like region. And that's a unique solution, because if I had 2 of them and subtracted them, the difference would be 0 over a finite interval, and I said there's no solution to something with one sign of energy and a difference 0 over a finite interval. So this is extrapolatable out into the times T2 less than T1 in the past light cone, and this is our answer for the amplitude in the past light cone. So here's the answer for the whole amplitude for everywhere. If T2 is above T1 in the forward light cone, it has to be this expression. In the intermediate, where T2 is outside the light cone of T1, it's either this one or that one. They're equal. And for T2 earlier than T1 in the back light cone, this is the right formula. We started by supposing something was relativistically invariant, and are able to deduce what happens when you go all the way around back on the other side. And that's not so mysterious. Suppose we had 4-dimensional Euclidean geometry. X, Y, Z, and W, all equivalent, so the sum of the squares of all those 4 things was constant. And we start to discuss rotations in that space. That's the analog of relativistic transformations in 4 space, okay? I can invert X, Y, Z, and W by a rotation. Because, for instance, I can rotate in the XY plane and change X to minus X and Y to minus Y. Another allowable operation is to rotate in the ZW plane and change Z to minus Z and W to minus W, see? 4-dimensional. So you can change all of them around. And therefore, once you've supposed the thing is invariant, you know where it is everywhere, even upside down. The only difference in the Minkowski space is that there's a kind of a no man's land where T2 and T1 are outside the light cone, and all the transformations can't really move you through there But we have obtained the correct continuation because the continuity is maintained by supposing that the energies are always positive. That limits the solution. In other words, this operation PT, which changes the sign of everything, is really a relativistic transformation. I should say more correctly, a Lorentz or rotation transformation, kind of. Extended across the mysterious space-like region by the demand that the energy is greater than zero. So it's not mysterious that we can work out the whole function. And it's not mysterious that relativistic invariance produces the whole works. Okay? So that was all right for spin 0. And now I'd like to do spin 1/2 and see what happens. There's a way of representing, once you start knowing that the thing is spin 1/2 and you have Lorentz transformations, you can work out by nice arguments about group theory exactly how all the states change and everything else. Without inventing the gamma matrices. Of course, you end up finding them, but it's all a group theoretic business, which I won't go into. It's a lovely exercise. But let's start out, and I'll give you some results of it rather easily. Anyway, first we just deal with ordinary rotations, and we know that if a thing has an angular momentum m along the z-axis and you rotate around the z-axis, the phase changes by e to the I m phi, and when it's spin 1/2, m is plus or minus 1/2, let's say plus, then it would be e to the I over 2 phi, and therefore a 360-degree rotation ends up by multiplying the function by -1. At this point, all attempts to do anything by instinct, by intuition, fail, of course, because it's hard to understand that, you know. I mean, one of the things that's the hardest part of this is to keep track of when you should have the -1 and when you shouldn't have the -1. Dirac had a very nice demonstration of this fact that rotation one time around can be distinguished from rotation. When rotation twice around is about the same as doing nothing. And I'll show you something you can find in dancing girls do. Here I'm going to rotate. Remember which way. Around, all the way around until you can see the blue mark again. And I've rotated 360 degrees, but I'm in trouble. I can't undo. But if I continue to rotate it still further, which is a nervy thing to do under that, I do not break my arm, I straighten everything out. And so 2 rotations is equivalent to doing nothing. But 1 rotation can be different. So you have to keep track of whether you've made a rotation or not. And the rest of this talk is a nerve-wracking attempt to try to keep track of whether you've made a rotation or not. I mentioned something else I'm going to need for shortcut to give you an idea of the nature of the formulas. If you want to, it's typical in this thing to have half-angle formulas. For example, the projection, if you would like to know with what amplitude, if it's up in the direction z, with what amplitude is it up in the direction z prime, which is at an angle theta, to z, the answer is cosine theta over 2, which is the square root of 1 plus cosine theta within a factor. Now we're going to do the same thing, adding relativity and going through this group theoretic analysis, which is I'm not going to do. I'm going to use a scalar coupling. I have a constant e squared minus p squared equal m squared as a constant, and that's like cos squared minus sinh squared, instead of cosine squared plus sine squared. So in this relativity, you have cos's and sinh's where you would have cosines and sines. In the other theory, and the energy would be m cos and the momentum m sinh of w. Now it turns out that these, oh, this should have been a W, right? Yeah. I can say it, and you don't have to actually do it. That the amplitude, for instance, if you started with spin up here and you ask with what amplitude you go into the correct a spin state in the direction P2, starting from rest at P1. P1 is m, the time component, and no momentum. P2 is e, the time component. Let's say it's moving in a z direction. The amplitude that you get is typical of the amplitudes for a half-angle spin, except they use half the the W, or rapidity, and the answer is to this problem is cosh W over 2, which is within factors which I'm not going to keep, like 2's and m's and things, is the cosh of v plus 1 square root. The amplitude to do that is this, and the cosh is really e, so this is the square root of e plus m. If you like it in a more relativistic form, consider p1 dot p2 plus m squared. By the dot product of two vectors, four vectors, I mean the product of the times minus the space components. And if you multiply the times, you get me, and all the spaces give 0. So p1 dot p2 is me. And here's a nice relativistically invariant looking expression. I mean, it's an expression for this amplitude in terms of p1 and p2. Now here's the thing that I wanted to say that we hadn't said before, but it's another important thing. I talked about turning everything over, but it's also possible to imagine that one of these vectors is turned over to be the opposite direction, and then we'd have a positron going into an electron. We have pair production. And we can calculate the amplitude for pair production by a continuous transformation of the formula that we have in terms of P1 and P2 until one of the p's is backwards. For example, if one of the p's is the positron, it would be coming in the other way, and if the positron had any momentum p and energy minus e, then the p2 vector that we represent it by, because we're drawing it upside down or backwards, is minus e minus p, where p1 is the same old thing, m. So p1 dot p2 is minus me. And it turns out that the amplitude for pair production, sure enough, is obtained by just substituting this value for p1 dot p2 in here. And by doing a little arithmetic within a sign, it's I times the square root of e minus m. And therefore, the probability of getting a pair is e minus m times some units, which are analogous to the scattering amplitudes. And this is a very interesting thing because it shows you how pair production rates can be calculated in terms of scattering rates by just shifting the vectors about. And of course, this is greater than 0. That's absolute square of that. Now, when we go and look at our pair case, where this was green last time, but I haven't got a green pencil, so it goes here, it goes this way, that's the one term, and then the other term goes backwards, and we tried to connect them last time by a kind of continuity. This time, because of this, if we went to the same state again, we get the square root of e plus m twice, and we get e plus m here. Well, how will it continue over here? Do you remember, if I didn't have the e in either place, that these two functions are the same in the space-like region? If they're the same, their derivatives are the same. So what fits together is the derivatives. If you take the derivative, let's say with respect to T1, T2, for instance, that would produce an E. And this, in the same place, would produce a minus E. That is the signs, hey. Well, that's wrong, okay? This one is backwards. This is T2 minus T1. Right. And the derivatives have opposite E. So this continues into that. Now what happens? I can't move. You see, everything is forced on me, all right? No tricks. Now we go to look at the real part of this one, and it does the same thing as it did in the case of the boson, and it produces the right rate, which is the square of this, which is E plus m. But then when I look at the real part of this one, it doesn't produce the right rate. It produces the rate minus E plus m instead of E minus m. It's the opposite. It's the reverse sign of the Bose case. Therefore, the real part of this number 2 diagram this time is no longer the negative of the probability of producing a pair. It's the positive of it. It's a reverse sign. I mean relative to the Bose case. Now, you remember what we had to have for the Bose case, that because this thing was coming up very strong negative, we had to increase the probability when there was a particle present. Now it's coming up with the wrong sign. That means we have to decrease the probability when there's a particle present. And this indicates why it is that the thing works. It all fits together only if you say that when there's a particle in state 1, the probability of producing another particle in state 1 by a pair production is decreased. Instead of going up to 1 plus 1 equals 2, as in the Bose case, it goes up to 1 minus 1 equals 0. In the Fermi case, and the rule is that they have a particle in a state, you can't make another particle in that state by a pair production. And the fact that that particle is preventing something that you expect it to happen from happening shifts the probability the other way, and it fits with the fact that the sign is reversed. And so you see, at this level, we have a completely clear clue that we are going to be able to demonstrate, in fact, we have for specific examples, the connection between spin and statistics, and that is different for spin 1/2 than it is for spin 0. In fact, what happens is, it turns out, I mean, it's rather interesting. It's very curious that you can make any functions that match in that region. It was the luck that we were able to do it. If you take more complicated functions, they won't match. That is, the positive frequencies can't be matched exactly with the negative frequency, because the positive frequency piece has two components, the real and the imaginary, and the negative frequency one will have to fit both, which is too much. So it's just luck that it worked. The only thing that will continue to work is if the functions are matched, their derivatives match and higher derivatives match. So the only thing you can put in here are polynomials in the numerator. And that's one of the reasons that for years people have been stuck with quantum field theory, in which all the couplings and all the propagations involve gradients, and more gradients, but never non-local couplings, because they just drive them nutty because they can't make this thing fit. So that we learned something else while we were at it. Okay? And the first thing that happens, you see, the scalar case is just a constant. Then if it's linear in the momenta, that means the square root of momentum on each side. Spin 1/2 is sort of splitting the linear thing. If it's quadratic, that's a spin 1 object going across, and so on. And it alternates like that. And depending on whether it's an odd number of powers or an even number of powers, this sign gives me trouble, or it doesn't. It alternates, and it's all nicely fit together. And again, I should be finished, and it would be wise to stop. But perhaps you'd like to see a little more general detail about how that sign comes about in a more clear fashion. And so what I would like now to write is the general rule that connects the particle and antiparticle. We said it quite clearly that you look at it backwards. To be more precise, the following is true. An antiparticle going from an initial state of momentum pi and energy ei in a certain particular spin state, ui, even if it's not spin 1/2, whatever spin it is, spin 1, whatever, 0, that's no spin. Starting in that state, and do various things. For example, it could emit a photon of polarization A. I just made a little example of the momentum q, energy omega, to end up in a state of momentum pf, that's this one, with its energy ef, and with another spin uf. This happens with the same amplitude that a particle does something. And you just have to do the particle by looking backwards. Right? The particle starts in a state of momentum pf, ef, and the spin, which is a reverse, the pt, reversal of uf. Actually, the p isn't going to make any difference, but just mainly the time reversal of the spin. It absorbs a photon of polarization, it comes out minus a star. I'll explain why. Momentum qa. It has to be a star because when you emit over here, you have the coupling a star, but you're going to talk about absorbing it. Why? Because the momentum's going the other way. You see, it's picked it up instead of dropped it out. And so it's an absorption instead of an emission, which is the time reversal, okay? In other words, it's time reversed, and it's to end up in a state of momentum pi-ei, and here's the key, and the spin state, the inverse of pt times ui. Why is it the inverse? Because in this first thing, we're turning one way, and then the second one the other way. So if we made a pt turn this way, and then we make an un-pt turn. In other words, one's a time reversal, and the other's the inverse of a time reversal. Sounds the same, doesn't it? All right, we'll come back to that in a minute. As a matter of, just let me make some notes here first. First, if I had an object of momentum p, the time reverse state would have momentum minus p, huh? Right. But then if I use a parity that I changed all the axes, the minus p would be flipped back to p. So that's why it's still the same momentum. In other words, what we're doing here is the c that is changing from particle to antiparticle is equivalent to parity change and time change. Everything is done in the reverse order in time. And if you work out the time reversed polarization, you discover, for instance, if you had circularly polarized light with the electric field going around one way, you have Ex equal 1 and Ey equal I. If you take the complex conjugate of it, it goes around the other way, the electric vector, and that's the time reversal and so on. So everything just fits together to make this exactly the statement that this is what's happening. Instead of particle antiparticle, that's the C, but everything backwards in time and everything reversed in space. And I'm not going to go into details to prove it any further. Now, the little difficulty is that here we have a state pt ui, and here we have pt to the minus 1 ui. I mean uf, and here's pt to the minus 1 ui. Later on, we'll want to go from a state to the same state. So it's much better to have the same system. So if I had a state ui to going ui, I want to have pt ui to pt ui. So I'm going to change this pt to the minus 1 ui to pt ui because I'm going to show that for spin and a half, see, if the states are the same, the in and out states are the same, then we can check the signs of the real parts very easily because they were the same previously. However, for spin and a half, I'm going to show you that pt reverse, negative, inverse, is the same as minus pt. In other words, by the way, you can choose the p phase the way you want, but let's choose it so that p squared is 1. So there's no problem with the inverse p equals p. So what we're going to show, t to the minus 1 equals t minus t multiplied by t means we're going to show that t squared is minus 1 for spin and a half and plus 1 for spin 0. And when I change this to pt, I have an extra minus sign for spin and a half, and that's where it all comes from. Why should it be that the sign, that changing around t twice changes the sign of spin and a half? Because a 360-degree rotation changes the sign. And if you can think in space-time, huh? Foink, foink. It's t twice, right? Turn it around twice. It should be 360 degrees. Oh, yeah, in some crazy xzt space, but smells right, doesn't it? I mean, if I flip the x-axis twice, I would be rotating 360 degrees. Maybe it's true of the t-axis, too. And that's what I want to prove. I want to prove now that it's true that if you make a time reversal twice on a spin and a half particle, you get the same state with a minus sign. In other words, 2 t's is the same as a 360-degree rotation and changes the sign. That's where it all comes from. This is, in fact, so elementary, and it should be an elementary physics textbook because it's so much fun. Having to do with time reversal. I have here a list of states, and here they're time reversed states, and here they are twice reversed. Let us call a state A. The state might be a particle doing this. No, that's too complicated. Particle doing that. And then the state TA is a particle doing this, okay? Or a particle with momentum this way would be A. Then the TA is a particle with momentum that way. All right? So TA means, this is Dirac's notation, okay? And this is the name of the state. And what I mean by this is simply the name of the state. I'm describing the name of the state, the time reversed state. For instance, a particle, and if I do it twice, I get that. A particle located at x, time reversed, is still located at x, no big deal. So this is this. A particle of momentum p, we just said, was a particle of momentum minus p when you reverse it. So, but a particle of momentum p can be made by the superposition of particles at different x with the phases as given. The minus p would be with the opposite phase. And so we discover that time reversal is what's called an anti-unitary operation. You must take the complex conjugate of the coefficients whenever you see them. For instance, if there's a state alpha A plus beta B, a superposition with coefficients that need not be real, then the time reverse state is alpha star times the time reverse state of A plus beta star times the time reverse state of B. And that's the general principle of time reversal. Now, if I could take the time reversal again, with x, it goes to x with minus p. Change the sign again, it's p, so that's okay, nothing happened there. And with this one, it's alpha times TTA plus beta TTB. Why? Because I take the complex conjugate twice, and if you're very good at algebra, you know doing that is a waste of time. Now, this state, of course, being twice time reversed must be the same state again. It's, you know, like a 360-degree rotation. You do it twice, it's the same physical state. And the damn quantum mechanics always permits you to have a different phase. So you can't say that this thing is the same state as that, but you can say that this thing is a phase times that. And that means that TTA is e to the I phi, that is, I wrote badly, a phase times A, e to the I phi times A. And all the states have the same phase, so that this interference that I have here will be the same interference there. So there's a universal phase shift when you take double time shift. Now let's look at spin. A half. Let's take the state which is spinning up in the z direction. Well, first let's talk about spin. It's spinning. What's the time reverse? Spinning the other way. All the spins have to be reversed. Every state goes into the opposite physical state. Let's start with the state up in the z direction. It'll go into the physical state down in the z direction with some phase. It's easy to prove that this, you can start with any phase and it all comes out the same in the end. This phase I'll choose to be 1. So it just comes out that the time reversal of the up spin is the down spin. Yeah? Yeah. Now the time reversal of the negative z spin is a phase times the positive z spin, of course. And we're going to show that the phase must be negative in just one moment. Because let us consider the linear combination, which is plus and minus. This should have been plus z and minus z if I wrote that out so carefully. If you superpose equally this one and this one, you'll get the state representing positive x. If you do them with opposite sign, you get the state negative x. All that should be known to the elementary student of spin. Now let me suppose that I try to say that the time inversion of minus z is the state plus z without that minus sign. Then do you see that the time reversal of the state plus x, this plus will go to minus and this minus will go to plus, will produce the same state again, which is not right. It's supposed to produce the opposite state. And therefore I have to change the sign here. Otherwise, when I did the time reversal, I would produce the same state. Well, if you put the minus sign in there and watch what happens, the plus goes to minus, and the minus goes to minus plus, if you can understand such a horrible thing. And if you look at it a bit, you'll find that that's the negative of the spin in the minus x direction, and that's where the negative is just a phase, and the spin in the minus x direction is what we want to reverse. Hence, it's necessary with spin a half that if the time reversal of the plus state, up state, is the down state, that the time reversal of the down state is minus the up state. It's so much fun. Now we do it again, huh? Well, we just learned that the time reversal of the down state was minus the up state. And here we learn that the time reversal of the up state is the down state. Now to keep this minus sign going through. So you see that if we do 2 time reversals, we change the sign. So it's just necessary, and there's nothing, it wasn't space, but we did it 2 reversals of spin, 2 time reversals, and you change the sign. It's equivalent to, it's just what you would do if you rotated 360 degrees. For a particle of even spin, which can have a state with a component along the z-axis of 0, the time reversal of that is still 0 along the z-axis. Any positive spin will turn negative, but the 0 will be 0. So therefore, the time reversal of this state, some j that's even, I mean integral, with the m equals 0, will be some phase times the state with the m equals 0. But if you do the time reversal again, I got the time reversal of this is e to the minus I phi times the time reversal of that, because of this alpha star. But the time reversal of that is e to the I phi, and these phi's cancel out, and you get the j m equals 0. So therefore, 2 t's on a integral spin is plus 1. In other words, 2 t's has the same effect as a 360-degree rotation. Okay. It's minus for spins a half integral spin, and it's plus for integral spin. How did I get here so fast? Okay, then I got them in the wrong order. Nope. Now when we look at the sign of a loop, I'm going to talk about the loop that had the contribution that was supposed to stop the vacuum. You remember, if you have a potential present, you can produce pairs. Therefore, the probability that you don't produce pairs must be less than 1. And you have to get the sign of the loop right so that 1 plus those loops is less than 1. In other words, the real part of the loops must be negative. And what you have to do that is when you have Bose, you have 2 particles coming out and going back into the same state. You have to have exactly the same thing with the positron and the electron going out and coming back in the same state, as indicated here. And I've written it out more carefully here. The amplitude is 1 plus x, where x is the contribution from this loop. Its real part times 2 must be negative and cancel the probability of pairs are produced, so that the sum of the probabilities over all alternatives remains unity. And that's going to determine the size of the thing. Now, to get the sign of the positron propagation to be right, just like a particle going from a state to the same state, we saw that we have to multiply by an extra TT. Otherwise, we'll have the wrong contribution of positron, have that extra minus sign. In other words, we have to multiply by minus 1. That is, the x is the loop trace times minus 1. One way of seeing it is that the way you want to go, coming out and coming back, is to change the time once and change the time again as you go around the loop. And that changes the sign. I pointed out earlier if the loops had minus 1 that we would have Fermi statistics, because you have 2 loops or 1 loop, and if there's a minus on each loop, when you made the exchange, you change the sign. It's interesting to realize that when people first figure out this loop, there was an ambiguity that no one seems to have worried about. It goes something like this. You're supposed to start in some state and then propagate around with all the couplings and everything else. And then they ask, are you in the same physical state? And everybody puts the U bar there, the U conjugate or whatever, and sums over all states. That becomes a trace. But the same physical state might be minus U. Maybe we've turned by 2 t's, and indeed we have. Because in order to get this the way we want it, we have to have the 2 t's in succession. And so it should have been minus u that we multiplied. In other words, we have minus the trace of the propagator. The kind of a circle that I mean here is that 2 particles are coming out in some state and coming back in the same state. I can represent that, if my pants don't fall down, by a belt of this kind, where this one went around one way and this went around the other way. But you see that that is 2 time reversals. It's a 360-degree rotation. And so when there's an odd number of pairs of t's, I count that as 1 TT, okay? An odd number of 360s, the contribution should be positive. That's the case I want. And when there's an even number of TTs, there's extra TT in it, the contribution should be negative because the extra TT makes it negative. This signs plus and minus are relative to what happens with the Bose case, in which they're always positive. So what we have discovered is that we have to put a minus sign in front of the traces of the propagators for the spin-a-half particle, and therefore that produces, as indicated before, a minus sign between 2 diagrams. I think I have another picture of those where you have 2 loops or 1 loop, and the minus sign comes twice with one case and once with the other. When you exchange something connected with two loops, it becomes one loop. Mr. Finkelstein, David Finkelstein, always makes the following demonstration, which bothered me for a long time because it sounded like it was very important, but I couldn't get all the signs right and straighten it out. But suppose you have two loops. I can't make it out of one belt, but you imagine the other one here. And instead of connecting them that way, I connect them crosswise. You see here, this goes over to the other loop, and this loop comes over to this side. Right? And you put them together. How many turns do we have? Okay. Well, you see there's an extra one in there. The loop I wanted went around straight. That's the plus one. If it has an extra turn, it's minus. And so this one's minus to what you would have expected. And that's the reason for the sign change when you exchange the particles. If you want to understand that it really is two turns, you try to get, if I can ever get it back to where it was. Yeah, well, here's the way it was on my arm, I think. And you see that if you go around once, twice, you see. T, 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 which is 4. And there's 2 extra T's, and there's a minus sign. So everything's okay, and I think I understand Mr. Finkelstein's demonstration now. Finally, I would like to show you an example in which we have a spin-a-half object in which we know where the angular momentum comes from. And that's fun. Suppose that we had a thing that Dirac invented, and it's therefore appropriate in this lecture, a magnetic pole. And suppose we have a charge, Q, and we'll suppose that these particles, the magnetic pole and the charge, are both spin 0. So we don't have to worry about any intrinsic angular momentum of either of those two things. But they're in each other's presence. And here's the magnetic pole, and here's the charge, and there's springs from one magnetic field in all directions, and from the other electric field in all directions, and they cross each other and make a pointing vector, which is momentum, which goes around this way, and sure enough, the thing has angular momentum. And the angular momentum is independent of how far apart they are, because if you started this way and moved them in and out, there are no forces, so there's no angular momentum. And you can figure out what the angular momentum is very many ways, and I'll leave as an exercise this. Suppose that it's along the axis. I'm going to show that it's E mu. Q mu. Q is the charge and mu is the thing. By this, suppose you try, here's the magnetic pole and here's the charge. Suppose you want to move that axis. If you move that axis, you've got to move the charge through a magnetic field at a certain velocity, yeah? And that produces a sideways force, which produces a torque, and then you multiply by the time interval, and that gives you the change in angular momentum. And that turns out to be just the change in the direction times E mu. So the angular momentum is E mu, and I'll let you prove it. I wrote EQ. That's very wrong. I changed my charge. Gee whiz, that's horrifying. It should be Q. Okay, the charge is Q, and the pole is mu, and the angular momentum is mu Q. And I got it right here, except to here. I also have another way of checking that the angular momentum, if we choose E mu equal to half h, we can have a quantum mechanical system. Dirac showed no other, only multiples of that are allowed. We'll take the smallest one. There can't be any other value because angular momentum has to be quantized in quantum mechanics. And so there has to be a relation of the pole and the charge. But it's kind of fun to test out whether rotating 360 degrees changes the sign. So imagine this is the magnetic pole, and there's a kind of a needle that goes out for miles. This is where the pole is, and here's the charge, and I'm going to take this little dion, the charge and the pole, and turn it all the way around and see what happens. Well, when you carry a charge through a magnetic field, the phase changes by e to the I times the charge times the line integral of the vector potential. It's a famous theorem. Now, if we carry that thing, that's supposed to intimidate you. That's Bohm and Aharonhof made a lot of that. Now, if we carry this charge all the way around the circle, we have the line integral of A around the circle. And the line integral of A around the circle is the flux. There's some kind of theorem, you know. Integrate A is the curl of over the surface, blah, blah, blah. It's the flux. Now, what is the flux? If I take the positive cap here, it's half the flux that springs out of mu, because the other half goes down. Springing out of mu, the flux is 4 pi mu. No, mu over r squared times 4 pi r squared is the flux, so it's 4 pi mu. So it's half of 4 pi mu. So e to the iq times the flux is e to the iq 4 pi mu over 2, and if I did it right, it's e to the 2 pi mu q, but mu q is a half. It's e to the I pi, which is minus 1. In other words, sure enough, if you rotate it 360 degrees, it's minus 1. It's a spin-a-half object, no problem, it's absolutely right. By the way, incidentally, the reason why it has to be quantized is if I had taken the flux below, I should get the same answer, right? No reason. How do I know where to take the flux? One is positive and another negative. So I could have gotten e to the minus I pi, which would be different. Oh, no, it's not. It's the same. E to the minus I pi is minus 1 also, so it's the same. And that's why you can quantize it that way. Now, imagine two of these things, one charge and pole, which I'll call A, charge and pole, which I'll call B, and exchange them. Nothing should happen because the charges don't do anything and the poles don't do anything because they're spin zero. Yet the things have angular momentum of half. What happens? What happens? Well, watch. As you carry this B around an A, think of it relatively. The charge on B is moving relative to the charge on A. So if A were kept still to look for the relation, you'd see B would move around to the other side. I mean, relatively. They'd go like that, right? It starts over here and it ends over there, but I don't want to move this, so I just do that to picture it. So we find A going around, the charge going around this way. Meantime, back on the farm, the other one, its charge is moving around B. So if B is held fixed, you find that charge A is going around B in this direction. And so there's a phase change, which is the integral of the charge, e to the I QA, you know, the line integral of the vector potential from here to here, and an additional phase change from the other one, which is the line integral from there to there. No matter what the shape of this line is, after a little thought, this line is a kind of mirror of it, of course, right? And therefore, you're going around something which splits the space 50-50, and the line integral all the way around is again the flux, and found out the flux was minus 1, half flux, half flux. And so you get from these phase shifts, from the mechanical efforts of the charges moving through the poles, an extra factor minus 1. And so when you compare what you get straight and what you get when you move them, you have to multiply by minus 1. In other words, this time we discover that this time the sign comes from the fact that when you exchange two things, one relative to the other, plus vice versa, has a 360-degree rotation in it. You know, it goes around altogether. Charges are moving 360 degrees around each other. And then it works. And so I would like to summarize the whole thing by saying, when two charges are exchanged, there's an implicit rotation of 360 degrees. We have noticed it inside with those productions and so on in terms of the T's and stuff when we recross it. But when you exchange two charges, there's effectively somewhere hidden in there, if you analyze it carefully, a 360-degree rotation. And it's this, if the spin is a half, then the amplitude must be changed by a factor minus 1 because of that 360-degree rotation. This experiment was to show the extra twist, which I already did for you. And that's the key to the factor of minus 1 that comes in the exchange of fermions relative to what happens in bosons. But to summarize it, although we went a long distance into detail, it's interesting to remember what we did, because it's not much If you suppose there's only particles and things can only go forward, you find yourself impossible to avoid going into the outside the light cone. This cannot be for only positive time because that depends on coordinate system. So therefore there must be something outside the light cone for the negative times too. And therefore the path that went forward from a different point of view has to go backward, and we find pair production. Then when we took a very simple example of a charge, all we had to do to discover that there's hidden in this works, when you go to put it together, the keys to spin and statistics is in considering in this diagram, that when you're calculating the sum of the probabilities, that this diagram has to be effect. In order for this to be here, you have to have an effect on the probability of producing a pair that depends upon whether another charge is present. An answer which comes out positive for bosons and negative for fermions. And it comes out negative for fermions because fermion has got a kind of a linear term in the propagator, and the linear term changes sign relative to this as you flip over, and so there's a minus sign. That contains everything, and the rest of it was just elaboration. Thank you very much.
I call on Professor John Taylor to propose a vote of thanks.
I can imagine a history of science examination question about the end of this century saying compare and contrast Dirac and Feynman, and he's given us some scope for beginning to answer that question today. The work of Dirac and Feynman has been interrelated in the most extraordinary way. And Feynman has given us today a talk which beautifully shows a lot of these key points which these two men have worked on. He's come over 9 time zones, I think, to give us this lecture, and will presumably return over 9 time zones. And I hope there isn't a minus sign in that. We're very grateful to him for coming. Thank you very much.